So in this talk, we're gonna talk about the deploying, testing fail-safe system with Yocto, me and Bruna. I'm an embedded software engineer here in Brazil. I do software consultancy. I do this for 10 years now, 10 years plus. So, well, I will leave to Bruna, then I will come back during the talk.
Sorry, I was on mute. I'm Bruna. I'm a software engineer. Sorry, I'm a little bit nervous. I'm an embedded developer at MC Logic since 2019. A little bit about MC Logic is a Brazilian company. We have over 7 years of experience in the marketing. We provide consulting, training, and software development services for microcontroller and microprocessor systems. We've already trained more than 250 professionals through corporate and online courses. And we have experiences in projects in the medical, agricultural, industrial areas, etc. Here in the slides are our contacts if you need it. And I'm going to start giving an overview about ELISA. Our goal to this presentation is show how we can apply ELISA's directives to Yocto. So ELISA stands for Enabling Linux in Safety Applications. It was launched in 2019, so it's a fairly recent project. And it aims to define a common set of elements, processes, and tools that we can integrate into our Linux-based systems for safety certifications. It is organized into horizontal work groups, safety architecture, tool investigation and code development, Linux features, open source engineering process, and systems. Here is an adapted diagram from ELISA website, and it shows an example of a reference architecture proposed by ELISA to construct Linux safety critical systems. We reference the Yocto Project as the foundation due to its reproducibility, which is crucial for safety certifications, strong community support, and its capacity to deal with the growing complexity of embedded systems. Then we can separate the applications at the processor level using virtualization systems within Linux and also using reference systems such as automotive-grade Linux that we will use to demonstrate later. And if the systems require solutions that are microcontroller, like often happens nowadays, we can integrate RTOS such as Zephyr. So why ELISA's directives are so important? First, embedded systems are more complex each year, and industry requires solutions that are faster, more efficient, and most of the time user-friendly. With so many variables to manage, the probability of errors, whether in hardware or software, becomes more significant. We need to be able to anticipate those potential errors, or at least fortify our systems to minimize it. One case we observed in our everyday work in our implementation is an example where the safety guidelines would be really important and involve a device with a touch screen that controls the application of a fluid. When the button on the screen was pressed, the fluid was applied, but there was no feedback on the graphical interface to confirm that the action and the application of the fluid really had occurred. So this was identified during tests, but it highlights a scenario in which the guidelines would be essential. So also, why these directives are important? Because one of the challenges for open source solutions is how to comply with safety standards and guidelines, such as those related to SBOMs, that we had a presentation today, as well to frameworks and requirements established by organizations like IEC and ISO. I don't know if any of you participated in this kind of accreditations, but it's really rigorous. So now, Fernando is going to present the more practical implementation of Yocto using the meta-elisa layer.
Okay, I will share my screen now. Just a second. You guys are seeing my screen? Everything's fine? Okay. So let's deep dive into the meta-elisa. So as Bruna said, ELISA creates standards and reference architectures for us to deploy safety critical systems. We're gonna take a look into the meta-elisa, and we're gonna show a demo using that layer. So first of all, some acknowledge here is in location to find this meta-elisa. So we can find in this GitHub, and these layers were created by the ELISA organization, which they have a dedicated working group to create this kind of layer. So what is the meta-elisa? So it's a layer dedicated to demonstrate how Linux can be used in environments with safety requirements. They focus on safety, monitoring, robustness of the critical application. They provide foundation for safety technology into Linux systems, and facilitate the development of secure and monitors systems. Some key components we're gonna see later, but we have the BSP part. We're gonna set some kernels configurations to enable a watchdog, for example. They have modification they added some recipes to monitor and to create a demonstration we're gonna see. And in these layers, for the example we're gonna show, the example is built on AGL, the automotive grade Linux. They use the version Needlefish of AGL, which is based on the Kickstarter of Yocto Project. Okay, this is the current release that they support. So they have some integration to the automotive cluster of the AGL, and then enable some monitors and recovery components. Next, there are some appends. You're gonna see some appends to the graphical interfaces to enable to trigger a warning when you have a situation that we have errors in the system. We can show that to the user. And we have some adaptation to the compatible device. We want to deploy it, and some enhancements on the user interface demonstration, and also the improved support for safety monitoring. So here I have the meta-elisa, all the layers and folders here, and we can see that we have some appends for the dashboard cluster of AGL. We have this safety demo, which is also an append for the safety cluster of AGL. They add some icons, and it's a patch for icons and things to show in the example. And most importantly, we have this pipe demo recipe here. This pipe demo, they have two services, two applications, one called signal source and another called safety app. The signal source will create for us, will mock the generation of signals. So as our demo will be about an instrumental cluster, we need some source of signals, like capturing the state of the car, the temperature, if the car is moving, if it's gonna make a turnaround, something like that. We can show to the user interface. And the safety app will monitor the signals, these messages. We'll check if the message is appropriate. We'll do a checksum and verify if this message is okay. And during the safety app, during this application is where we're gonna check if everything is right. If not, we're gonna trigger a safe state for the application. You're gonna see in the example in the next slides. And others, there's some images to build the SDK. Okay, there is this also. So one critical part of this example, and also for ELISA, for the safety guidelines, is to incorporate an external watchdog in our systems. So this is very, very common to be used in systems like medical device, automotive platforms. In the microcontroller space, this is very common. In Linux, we have also applications with watchdogs, but it's a little bit it's less common. Okay, so for this guideline with ELISA, the external watchdog is very important for us. So I'm gonna have an architecture like this. We have our kernel, we have the workload that we want to do, the use case that we're doing. And then we have a safety monitoring, some kind of software here that will monitor the workloads and will monitor the watchdog. Will be responsible to trigger this watchdog or not, to patch this watchdog or not. So this guy will make the safety monitoring of our application. For this example, we're gonna show, and for the meta-elisa, in the BSP part, we're gonna see that we use an Intel 6300 ESP chipset. We're gonna run the demo on a QEMU environment, not on the target, but we emulate this driver using QEMU. Okay, so this is the driver that we set on the BSP layer. So another features here is now talking again about the pipe demo recipes. So they install the safety app. You're gonna see this guy will monitor the application and the watchdog, and we have this safe signal source, which create for us the mocking signals. And also we have an application that we're gonna run on the command line that will trigger a message with errors, so we can trigger the safe state of the application. What else? This demo, the pipe demo is they build it using named pipes. So through communication, the IPC they use was this guy. But we also send messages through the CAN bus to the automotive cluster, okay, for the data visualization. So here is the pipe demo, just looking for this recipe. So you can see two services, and in this recipe, you can find the link to find the application we're gonna use it. So, okay, let's take a look at the demo. Just to my video here. Okay, so this is the demo I'm gonna show. So I'm gonna play and stop for each part to explain to you guys. So we have here in this top right, top left, the bottom left, the bottom right of my screen, I will start the QEMU here, and I don't know if you guys can see it, but I forward some devices to QEMU, especially the device about the watchdog here to emulate the watchdog. So here we start the QEMU. This is the screen of QEMU, the automotive grade Linux with the automotive cluster. Okay. Well, it's a standard automotive cluster, and now here I'm gonna SSH into the machine here that we are running the demo. So I'm gonna SSH there, and here I'm gonna show the logs. So this image is based on systemd. So I'm gonna use the journal CTL to monitor all the logs here. You can see that we have a signal source. So here we're gonna see what are the status. So there is corrupt message if there is skip message or they triggered a safe state. And here the safety app waiting for they receive this message, process if everything okay, they keep waiting. And now I got it now on the bottom right of my screen, I will trigger a corrupt message. So skip. Okay, so you guys can see it. Let's this a little bit. So here in the bottom, I'm gonna run a command line program called system source control panel. And this guy, they have a nice command line interface, and I will send a corrupt message to my system. So I will choose that. And here we can see in the logs here that we received the corrupt message. You guys now we're gonna see that the safety app will notify us that something has happened, and the safety application will stop petting the watchdog. So when the watchdog, if I remember correctly, is like 10 seconds or less. If the watchdog is not pet during this time, the watchdog will run and will restart the system. So let's keep. So you guys can see here some message of corrupting errors. Not a common message, and the system is rebooted. So this reboot was the watchdog acting on our demo. Okay, so this is like the simple demo we can do for using a watchdog and a monitor system to trigger this safe stage, and we can return our application to the initial stage that was a safe state. There's a little bug here that I didn't told you guys, but when we send the message, the corrupt message, it should show us here in the automotive cluster on the display the danger message that something had happened. But I don't know, when I built this, something didn't work. So I don't know if it's something changed on the AGL side, but the good news is the thing is working, is rebooting as expected. So okay, let's come back to the presentation. And for now, some final takes about the demo, and also about the ELISA with Yocto, what we consider good things. So I will start, and I will ask Bruna to give her points too. But one thing that we considered very, very interesting about ELISA and the standard they are proposing is that we can extend this, extend the application, the use case for others applications. Here in Brazil, we have many equipments on the agriculture side, the precision agriculture. This is not a critical safe application use case, but we can see that if you guys use a look to this application with safety in mind, maybe we can reduce downtime of one equipment. Imagine an equipment that is running on the field. So if the system break on the field, it's good to have something to bring him up again. So with that we can reduce. We can not reduce our productivity of the system in case. And also having accelerated reference layers like proposed from ELISA help us to accelerate products. So we saw with many clients that even all the clients go to the same conclusion in the end, but they start from the scratch. So having some reference, some guidelines to start the project is a good thing. To have a guideline, in our case, in Yocto, have layers supporting that to facilitate the time to market for the solutions. I don't know if Bruna wants to say something to complement.
I think you already said most of the points. The only point I would want to bring it back is the fact that when we read about ELISA, they say a lot about automation and health and medical in this case, and aerospatial. But ELISA can be applied to a lot of fields where, of course, it's not life-threatening as it is in the medical field, but it would help a lot to follow these guidelines. I think in any type of industry, but Fernando also already talked about that. I think it covers most of the things. Thank you for your time.
Yeah, that's
And
it. Thank you for your times. And if you guys have any questions, send us.